Hey guys, welcome. Yeah, so when you're starting your study of solving second order differential equations, this video should be the first video you watch, and there are 3 additional videos that will follow it to complete this introduction or the fundamentals to solving second order linear differential equations. Now, to start, we know that a non-constant coefficient second order differential equation would look like this, and of course if P, Q, R are all constants, then it would be a constant coefficient differential equation of second order that is linear. And I know a long name, but yeah, that would be this constant coefficient second order linear differential equation. That's this here. And if g of x is equal to 0, then it would make it homogeneous. If it's written exactly as I have here, when g of x is equal to 0, it means that we are considering a homogeneous constant coefficient second order linear differential equation. What a long name. But yeah, that's this here, right? Okay. And so the goal of this video and the next 3 is to teach you how to solve any and every differential equation that is of this form. Yeah? Okay, cool. So to start, let's consider an example of such a differential equation. Notice that this here is in fact of this form. A is 1, B is 0, and C is 1, right? And here, right? Otherwise, it's exactly of this form. And for this, we don't even need to develop any methods. In a little bit, we're going to come up with general methods for solving differential equations like these. So like a few steps, and then you'll see how to solve differential equations that look like this. And but that's methodically and by showing you why that method works. But for this one, we don't need any methods. We could just do it by inspection. That is, we can just eyeball it, right? Okay, and this is what I mean. Well, if we pay attention to the differential equation, what it's saying is, well, whatever function y solves this differential equation, its second derivative needs to be 9 times y, right? And so its second derivative will need to look very much like y, but different from it by a constant. What kind of functions y do that? Exponentials, right? Consider a function such as y equals e to the 3x. Right, this will exactly solve this differential equation. And why you say? Because, well, if y is e to the 3x, then its first derivative is 3e to the 3x, but its second derivative is 9e to the 3x. So the second derivative is exactly 9 times y if y is equal to e to the 3x. And so we see that this here, this y will solve this differential equation. And we also notice that there's one other y that will solve this differential equation, and that is this other guy, right? This too will work in this particular case, right? Okay, now, because this y here and this y are different, and because there's something specifically true about them, which I will mention a little bit later in this video, we say that these form a fundamental pair of solutions. These make a fundamental pair of solutions to this differential equation in this case. Yeah? Okay, and you will not know what exactly a fundamental pair of solutions means until the last video, so the 4th video. Yeah, and this being the first, but yeah, but it's okay, because, like, you know, if I went on a tangent to teach you what exactly it means to be a fundamental pair, then it might be like bad teaching. Wink wink. So yeah, like, we want to keep it to good teaching, right? Okay, now if you do have a fundamental pair of solutions to a differential equation of this form, then you're pretty much set, because the general solution is just going to be a constant times this one, plus a constant times this one. That's what we have here. We've got our fundamental pair of solutions here, constants multiplying each of them, and added together they make the general solution. And so we're saying that any y, right? Any function y of this form will solve this differential equation. So if you want it to look more like y1, what you can do is like make beta 0, and if you want it to look exactly like y1, make beta 0 and alpha to be 1. But yeah, these two and infinitely many other solutions to this differential equation are contained in this general solution. Now, of course, if the differential equation comes with some initial values or initial conditions, then we may be able to solve for alpha and beta and get the particular solution to the differential equation, right? Okay, cool. Yeah, let's keep it moving. And in fact, before I go on, notice that for this y or this y, writing a constant in front of them will not change the fact that they solve the differential equation. You can see that from what we have done here, right? But like, say like we take y equals 5 times e to the 3x, that too will solve this differential equation, because the inherent relationship we want here is for the second derivative to be exactly 9 times the function. And even if I threw a constant in front of this, 5 times e to the 3x will still abide by, the second derivative is 9 times 5 times e to the 3x, right? Okay, just giving you more insight into why, we could ignore the constants. Because basically, if I throw alpha here, find the second derivative, and then plug in the function with alpha thrown in front of it, I can factor out the alpha, the constant, and divide on both sides. And so basically, like, we don't need to have the constant in front of this in our analysis, is what I'm saying. Jesus Christ, I went like berserk and like justifying that, but yeah. What we just did here, if you notice, is we took two fundamental pair of solutions and we made a general solution out of them, and that's generally something you could do, and it's called the principle of superposition. And so if y1 and y2 are two fundamental pair of solutions to a differential equation, then so will be so if they're each solutions in their fundamental pair, then y equals, this will be also a solution to the differential equation, and the general solution will always look like this so long as y1 and y2 are fundamental pair. And yes, I know I said I won't say too much about fundamental pair. Well, that's not my exact language, but whatever. Like, I made promises about not talking about it again, but here, I'll say a little bit more, because, like, perhaps it's worth planting this seed, which is, like, you'll learn thoroughly in a future video that, like, to be a fundamental pair means that the Wronskian is not 0. But for now, in our example, the two y's, y1 and y2 that came up, are a fundamental pair. So that's all you need to know for now. Okay, and as I said, if you've got your fundamental pair of solutions, then the general solution is going to look like that: constant times one of them plus a constant times the other of them. Okay, all right. Now, we said a particular solution, right? And that you get from some initial conditions placed on your differential equation. So let's take the same differential equation that we just solved and impose these initial conditions. First one is saying that the solution y is equal to 2 when x is 0, and the second condition is saying that the derivative to the solution y is equal to 1 when x is 0. Okay, so these are what we're going to impose, and what we said from our work earlier is that this is the general solution, and so this is our y, and so y will equal 2 when x is 0 will amount to saying this, right? Y is equal to 2 when x is equal to 0 for this particular y, right, is going to look like this. Now, this says e to the 0, which is 1, and this too says e to the 0, so the equation reduces very nicely to this. And now, using the second initial condition, by taking y and taking its derivative I'm recognizing, and this is the derivative of y, I'm recognizing that when x is 0, the derivative of y is equal to 1. We get, well, first this here, and then we can clean that up a little bit into this here. Now you've got two equations and the two unknowns alpha and beta, and so this is simple algebra that's left to do, and so like I won't handhold you through it, but yeah, basically from this equation we could get alpha by itself is 2 minus beta. We can come here and replace this alpha with 2 minus beta, and then that means that we have an equation all in terms of beta. We solve for beta. Beta turns out to be 5 over 6, which means that alpha then has to be 7 over 6. And now that we know alpha and beta, we can come back and replace them with their actual value based on these initial conditions to claim that we've got the particular solution in this case, which would be this here, a particular solution to this differential equation given these initial conditions. Yeah? Okay, cool. And so the last thing we have to say here is perhaps the most important thing, which is, well, in the general approach to solving all homogeneous second order linear differential equations of constant coefficients, in the general approach we have what's called a characteristic equation, and it is crucial to the method for solving equations with very long names, as I just said. Right? And so then let's talk about this characteristic equation and a general approach, because if you haven't noticed, so far we haven't talked about the general approach to solving these second order homogeneous constant coefficient linear differential equations. Now, for this guy, it turns out that the characteristic equation is this. So you may get a sense of like how to look at second order. You get a blah 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 differential equation and then pick out the characteristic equation. So you may already be practiced at that just from looking at this example. But how exactly do we figure out this characteristic equation? For a most general, you get it, long named differential equation. I know the name, I just don't want to keep saying it. Okay. Well, we do this kind of like how we solved this, which is like we make an initial guess. Because again, we see that since what we've got involved are the function y scaled by a constant in its first derivative and its second derivative also scaled by constants, we want what we had earlier when we were solving this, which is that like we want y and its derivatives to look very much alike. And so based on that, we look for solutions of the form y equals e to the rx, and for reasons I already said, we don't need to throw a constant in front of the e. That is, we don't need to do this. I already talked about why it doesn't matter, right? Okay. But yeah, if this is our y for our guess of what solves this differential equation, so we already know this, well, we need to know this and this. So we get on to finding first and second derivatives, and so that's this guy and this guy. We plug all this information into the differential equation this, and so that would mean this. Now notice that every single one of these three terms has an e to the rx in it, and so I can factor that out and get this. Now, how did we get here? Well, we said that our solution y that solves this is e to the rx. If that must be true, if y equals e to the rx solves this, what has to be resulting truth is this, right? What has to follow is this, is what I mean. Okay, now if this has to follow from claiming y equals e to the rx as a solution, notice that e to the rx is an exponential, is never 0. So what has to be true if this is a solution is that this quadratic must equal 0. So then this here, this y will be a solution for whatever r solves this quadratic, and this quadratic here is what we call the characteristic equation, or the characteristic quadratic, or the characteristic polynomial. So very, very, very important. Yeah? Okay, the characteristic equation. So when we're solving differential equations of this form, and for reasons I already mentioned, I don't want to say the name, but yeah, we're solving them, the first thing we'd want to do is figure out what the characteristic equation is, because, well, from the characteristic equation we get solutions, and by the way, since the characteristic equation is a quadratic, three things can happen, right? which is we have 2 real roots, the subject of the next video, 2 complex roots, the subject of the video after that, and 1 repeated root, and that's minus b over 2a. This would be the 4th one of the videos that are important to understanding how to solve these guys, right? Okay, and this is the 3rd one, and this is the 2nd one, because the video we're on is the 1st one. That's how you count backwards. Okay. All right. So yeah, you know, you get to this quadratic, right? And that's why it's all important to pick out the characteristic equation. You solve the quadratic. Worst thing that'll happen is you have to use the quadratic formula. But yeah, you get 2 r values in this case and this case. And what happens is then you go, oh yeah, y equals e to the 1 of the r's. X is one of the solutions, y1, and then y equals e to the other r, x, is the second solution, and they will always be a fundamental pair in this case and in this case. Well, this case is a little bit more tricky because then both r's are the same, so you're getting the same y, but I'll teach you what we do in this situation in the last of these 4 videos, as I said. All right, I hope you enjoyed this, and keep watching. Take care.